Well, hello, welcome again to Math 315, Analysis and Topology. And this is the second video in the chapter 10, which is on topology. We finished off last time we're talking about open sets. Remember, a set was open if at every point in the set there was enough room to squeeze a little epsilon neighborhood, or in more graphic language, enough room to swing a cat. Just a little bit of quick revision of some set theory notation here in language, which I'm sure you've seen before, but just to recap that. So just to go over what we mean by unions and intersections. So if we're given two sets A and B, we define the union of A and B, which we write as A with a big U, B. And this is a set of all elements which belong to A or B, or possibly both. In mathematics, the word or is always inclusive. In normal English, it's often exclusive. If you say, I'm going to the beach or I'm going to the pictures, you normally don't do both. But in mathematics, or is inclusive. So you might be in A or you might be in B or both. So a simple example of that, if we take A to be the set ABC, B is the set CDE, then the union consists of all the objects that are in both sets. So A's in both take all the ones in here plus all the ones in here. So that's A, B and C. Now we've already mentioned C, so we don't mention it again, and then we add in D and E. On the other hand, we define the intersection of two sets A and B, which we write as A with the upside down U. And this is the set of all elements which are common to A and B. That is, they've got to be in A and in B at the same time. So simple example again, if we take A to be the set ABC, B to be the set CDE as we had above, then the intersection of these two, the only element that's common to both of these is C. The set which contains no elements is called the empty set. It's a perfectly good set, it's just got nothing in it. And it's written as 0 with a stroke through it like this. This is the empty set. So for example, if I take the set A, which is ABC, the set B, which is DEF, then there's nothing common to both of these. So we say that the intersection of these two is the empty set. So just a little bit of revision there of some set theory notation. And having that, then we can state our first theorem for this section. We saw in the example above that when we had two open sets, we saw that we looked at the union of the two open sets, and we saw that was also open. So here's our theorem, the first one for this section. It says if A and B are open sets, then so is A union B and A intersection B. In other words, that says the union of open sets is open and the intersection of two open sets is also open. I'm just going to do the first one here, and they're very easy to explain this. Really, it's not really a proof, it's more of an explanation. But suppose you've got A and B are two open sets. Then I pick something in this set A union B, and I have to show that there is an epsilon neighbourhood around A that's contained inside this set. Well, if it's in A union B, by definition that means it's in A or it's in B. Now if it's in A, then because A is an open set, there is some epsilon neighbourhood. There's enough room to swing a cat at A. There is some epsilon neighbourhood in A epsilon, for some particular epsilon, of A that's contained completely in A. And similarly, if A happens to be in B, then there's some epsilon neighbourhood for some epsilon that's completely in B, and that means this epsilon neighbourhood is contained in A or B, so it's in A union B. One can do a similar proof for A intersection, and the proof of that's similar. Now the above result for the union of open sets can be extended to the union of arbitrarily many open sets. And this is an important idea when we come to defining a bit later topological spaces. That is, if A1, A2, etc. forever is an infinite sequence of open sets, then the union of all of these is also an open set. Now this is not true for intersections. And so I've done a nice example here just to show you the difference between the two. So here's my interval, so my set. So A sub n looks like this open interval. It's -1 on n, comma 1 on n, where n is any positive integer. So let me draw a little picture of this. So if n is 1, for example, this will be the open interval -1, comma 1. So A1 consists of all the points inside this interval. If I put n to be 2n, I'll put 0 in the middle, then we get -1/2 up to +1/2. And that would be this open interval. Now, by the way, the union of these two, all of this and all of this, of course, is just the interval -1 to 1, and the intersection of the two is just this bit. Well, similarly, I can put 3 in, I'll get a -1/3 up to 1/3, -1/4 up to 1/4, and so on. And you can see then, if you take the union of all of these, they're all inside this interval -1, 1, so the union of all of these little intervals, as we move inwards, the union of all of them is just -1, 1. And that's an open set. So we can take the union of arbitrarily many open sets, and this turned out still to be open. However, if we look at the intersection of these two, the intersection of A1 and A2, as I mentioned, is just this little bit in here. And if I take the intersection of that one, and the next one in, well, it's just going to be the bit in here, between -1/3 and 1/3, and so on. And if I take all of these intersections of these infinitely many sets, then the only thing that's common to all of these is the number 0. That is, the intersection of all of these sets is just the set containing 0, and this is not an open set. Because if I take just the set containing 0, as soon as I put an epsilon neighbourhood around here, then I'll have points in there that are not 0, and so they don't belong to this set. So that's a very useful, very interesting example to think about, where I've got the union of arbitrarily many sets, open sets is open, but the intersection of arbitrarily many sets is not necessarily open. And we'll come back to this later when we look at what topological spaces. Now, you talk about open sets, you're probably thinking, well, what about closed sets? Well, are they the opposite? And the answer is no, because unlike a door or a window, the opposite of open in topology is not closed. In fact, you'll see you can have sets that are neither open nor closed. You can have sets that are both open and closed. You can have all sorts of things happening here. So the opposite of open is not necessarily closed, and we need to work out what it is. Well, to do that, firstly, we need this just to remind you about, from set theory, what we mean by the complement of a set. So if we're working in some universal set X, and we have a set A which is contained in X, then we define the complement of A, which we write as A with a little c up the top, to be the set of all elements of X that are not in A. So you can think of it in terms of a little diagram here. If we think of X as our big universal set, and I take the set A, which is, say, here, then A complement is all the things in X that are not in A. So this bit out here would be A complement. So A complement are all the things that are in X but not in A. And as a little example of that, just with some simple sets here, we're going to take the universal set here is going to be A, B, C, D, E, F. A is the set C, D, E. And so A complement are all the things in here that are not in here. So A is in here but not in there. So A is there. B is in here but not in there. C, D and E are in there, so we don't include those. But F's in there but not in there, so we have F. So ABF is the complement. Now, more important for us looking at the real line, if we take the interval minus 1, 1, again let me draw a little picture of this. Pictures are very useful always in maths. So I'm going to take A to be the interval from minus 1 up to 1. So there's A, it's that open interval. A complement then is the union of these two sets. So it's going to be all the things from minus infinity up to and including minus 1. And on the other side, it's going to be all the things including 1 going up to infinity. So on the real line, the complement of this open interval is the union of these two intervals, which by the way are not open. We can define then a closed set in terms of complements, and that's what we're going to do now, is to define a closed set in terms of complements. So we're going to say then that a set is said to be closed if its complement is open. A set is said to be closed if the complement of that set is open. So if we have a look and see an example, explain why the set 0, 1 is a closed set. So here's a little example of this, or solution to this here. So here's our set 0, 1 on the line, and I claim it's closed because I look at its complement. So this is the set 0, 1, including 0, including 1. So the complement of that are all of the numbers from minus infinity up to but not including 0. So that's going to be this interval. Union, all the things from 1 excluding 1, because it was included here, excluding 1 going up to infinity. And that's this set here. Now we've seen before then that the union of two open, these sets are both open, clearly. In each one of these there's enough room to put a little epsilon neighbourhood, and the same over here. So we've got here the union of two open sets. It's a union of two open sets, and hence it is open. So that tells me that A complement is open, and that means A is what we call a closed set. Now in reality, most sets are neither open nor closed. For example, if we take the set 0, 1, where we're excluding 0, including 1, this one is not an open set. Because if we look at 0, 1, again we'll draw a picture here. So 0, 1 is excluding 0 but including 1. It's not an open set because although you can put an epsilon neighbourhood at a point here, if I take the point 1 which is in the set, there's not enough room to swing a cat here. As soon as you put an epsilon neighbourhood, it's going to go outside of the interval. On the other hand, if you look at its complement, now the complement of this is from minus infinity up to including 0, and then excluding 1 up to infinity, well that's not open either because it includes the point 0, and there's not enough room to swing a cat at 0. So the complement of this set is not open either, and that means neither this set nor its complement is open, and that means this set is neither open nor closed. So that's a nice example just to get these ideas into your head. Note that the empty set, which we talked about a minute ago, this is open because it contains no points, and therefore we say that the definition is vacuously satisfied. That simply means that, well, the definition says give me an element inside the set, there's got to be enough room to swing a cat. Well, there are no elements inside the set, and so the definition is satisfied without doing anything, because there's nothing there to check. So we say that this is vacuously satisfied, so we say the empty set is an open set. Now, by the way, that means that the set of real numbers, well, the real line is open. If you take the whole real line, that's an open set. There's enough room to swing a cat at every point. If you take the complement of the real line, well, there's nothing, because the real line takes up everything. So the complement of the real line is just the empty set, and that is also open. So the set of real numbers is both open and closed. It is both open and closed. Now, in the next section, we're going to be looking at continuity, and we're going to try and capture the idea of continuity eventually without using any notion of distance, which we have been using thus far. But to get to that point, we're going to try and see what functions do and what continuous functions do to open intervals. Now, in order to get started with that, we need to get this idea of the image of a set. So in calculus, we use the function notation fx, or f of x. This means we take a given function f, which is some formula, and you plug in a specific number x, and you get a new one, f of x. So we use this notation f of x to denote what a given function does to a specific real number. Well, we can extend this notion a little bit to see what a given function does to a whole set, not just a particular number, but to a whole set. And I'm going to write this simply as f of a. We're going to use capitals for sets generally. And I'll finish off this by doing an example here, which I will do over here. So here's the example. We take f of x as x squared, which our old friend the parabola. We want to know what's f of a. Firstly, if a is the interval 0, 2, and then if a is the interval minus 2 to 0, union to 0 to 2. This, of course, is just the same as the interval minus 2 to 2. So here's the little solution to this. So here's our function, f of x is x squared. Let me draw a picture again. So there's my f and there's x. Now we've got firstly the set a, which is 0, 2. So we're taking this interval here on the x-axis. And we're going to see what happens if you take all of the numbers in here and you square them. Well, 0 squared is 0. 2 squared is going to land me up here at 4. And all of these numbers in between will correspond to numbers here. So, for example, if I take 1, that's going to map across to 1. And you can see that all the numbers in here are going to get mapped to all the numbers in here. That is, we're going to say that f of a, f of this set, of this closed interval, is equal to this closed interval, 0, 4. For part B, we're looking at a is now going to be the union of minus 2 to 0, union 0 to 2. Could combine these, by the way. I should have, I think I had square brackets there. I better be careful with my brackets. So we've got brackets there, square brackets both sides. By the way, this thing here, of course, is just the set minus 2 to 2. You can combine these together, of course, because 0 is a common element. Anyway, if you look back to the picture, if we look at minus 2 to 0, if you take all the numbers in here and square them, well, again, they end up here. Every number in here, if you take minus 1, that's going to end up also at 1. Take all the numbers in here and square them, they're going to end up here on this axis. So f of this set, so I should put f of a there. So f of this set is going to be 0, 4. And f of this set we also saw was 0, 4. And of course, if we take this, this is just 0, 4. So f of this set, or if you will, f of this set, is just equal to 0, 4. Now in the next recording we're going to be looking at what happens. Can we go backwards? Can we look at the thing from the other way and look at what happens if we start off here? How do we get back to the x-axis? And we'll have a look at that in the next recording.